Dr. Rico here. This is a lecture from my course on robotics. The syllabus link is in the description. Okay, deliberative robot control architecture, part of the robot control architectures chapter. Here we go. Deliberation connotes a complex process. In the sense, decide, act robot control schema considered before, it means the decide step includes so much complexity that we now call it plan. That is, sense, plan, act. This planning often takes the form of extensive modeling of the robot and environment that extends into the future. Early robotics, under the influence of early AI, was focused on this type of robot control. Major drawbacks that quickly emerged were the large runtimes and constant deprecation of environment models, in changing environments at least. The architecture of reactive control was introduced to solve these and other challenges for deliberative control. However, planning remains indispensable for modern robots. Modeling and planning. Models of a robot and models of its environment are usually quite different. The primary difference is that usually an environment model is static, except in that it may be updated from measurements. For mobile robots, such models are often in the form of maps. You're familiar. Spatial models of the environment. Planning with such a model usually takes the form of planning routes from one location on a map to another. In contrast, a robot's self-model is usually time-varying in that its state is constantly being updated via measurement. Moreover, a self-model is usually mathematical and sometimes even dynamic in the sense of Newtonian mechanics. This provides a distinct advantage for planning. A mathematical model will typically give the robot foresight. A robot can thus plan its actions in such a way as to make likely the achievement of its goals. Foresight is, of course, a key aspect of intelligence. Consider a controller with a model of itself and its environment. The set of all possible states for the robot environment can be considered a state space, one state of which can obtain at a time. Many planning problems consist in selecting a path through this state space. If we include a time metric along the path, it is called a trajectory. As illustrated in the figure over here, a path or trajectory through this robot environment state space starts at an initial state S1, so right here, and ends at another state S2, sometimes called the goal state. This might be a mobile robot moving from one location to another, or it could be a manipulation robot changing configuration. In any case, the path from state S1 to another S2 is a sequence, potentially infinite, of intermediate states. So if we took this particular path here, then we would be going from this state to a state here, to a state there, to a state there, to a state there, etc. And if it's a continuum, then of course there are an infinite number of them in between. Planning, then, consists primarily in choosing this sequence of states. A planning problem can have one, many, as shown in the figure, or even zero solutions. Usually there are many, and the question becomes, which path is best? To answer, we need metrics such as a path duration, path length, preferable subsets of the state space, etc. What the planning problem frequently amounts to then is path optimization. Optimization is like a whole thing. It is an area of specialization in mathematics, artificial intelligence, and control theory. And all of these fields play roles in robotic planning. I encourage you to take a deeper look at planning by checking out the first 5 chapters of the Bullough and Smith lectures, potentially in its book form, as I have hosted here. So I encourage you to check that out. It includes my lectures over at least some of the chapters. All right, that's all I've got. Thanks.